Okay, so a base is to OH minus as an acid is to H plus. A base has the ability to create OH minus, an acid has the ability to create H plus. So our mice tables are going to look very similar. Our calculations are going to look very similar. And the only thing is that we're dealing with a base and dealing with OH minus. And so we have an additional step to convert pOH to pH. Alkali metals include lithium, sodium, potassium, cesium, rubidium, francium. And they all create soluble hydroxide compounds. And so these are the strong bases. Lithium hydroxide is the one that we're going to deal with here first. And it dissociates completely into lithium ion and hydroxide ion. Written on the bottle would be 0.05 molar. What we really mean is that we have 0.05 molar lithium ion, 0.05 molar hydroxide ion. If I take the log but change the sign of that log, I will get 1.30. But that is the pOH. I'm asked for the pH. And so I take the number 14, subtract 1.30. I have 12.70 as the pH. pH plus pOH. 14. Why? Well, because H3O plus times OH minus gives me 10, 1 times 10 to the minus 14. Take the log and change the sign, that's where I get 14. Take the log and change the sign, that's called pH. Take the log, change the sign, that's going to be called pOH. So that is why those things are all related. Okay. Our Kb is similar to Ka, but instead of producing H plus, our base produces OH minus. Now, here's a problem in which we have a stated pH there, and we are asked to determine the Kb. Before we go any further, let's make sure that we understand that Kb is going to be equal to the products of the reaction that we're looking at divided by the reactants, all given as concentrations. But we don't know any of these numbers just yet. What we do know, however, is the equilibrium concentration of OH minus. 14 minus 11.55 is where I came up with 2.45. That is the pOH. I take that number, changing its sign, raising 10 to the resulting power, and I have the concentration of OH minus, getting 3.5. 3.55 times 10 to the minus 3. That number goes here. Now, it's true that in neutral solution, this is 1 times 10 to the minus 7, but that 10 to the minus 7 is much smaller than 3.55 times 10 to the minus 3. So in fact, I had to add 3.55 times 10 to the minus 3 to get to 3.55 times 10 to the minus 3 at equilibrium. Now, this is a Mice table, and since the coefficients are all 1, this is also 3.55 times 10 to the minus 3. This is minus which is 0.1964. I'm going to round that off. Notice this number is a little bit lower than the one I started with. So since I've got all those numbers to 3 significant figures, we use them to 3 significant figures. this is the concentration of both the hydronium ion and the conjugate acid. So I'm just going to square that number. But I am going to put in the number I just calculated. That is slightly different than 0.2. My Kb is now equal to the square of the number we were just calculating divided by 0.196. I end up with 6.4 times 10 to the minus 5. So Ka and Kb proceed by the same process. The only difference is that Kb is involved with OH minus and Ka is involved with H3O plus. Our manipulations are the same. Our mice tables are going to look pretty much the same. We just have to pay attention to the fact that this is not the same. Whoops. This is not quite the same as that. They are related. They are related through this thing called Kw. Their product is 1 times 10 to the minus 14. Okay, this one is a tricky one. We are very infrequently given a list of Kbs. We will, in class, talk about a list of Kas, but how on earth are we going to deal with this equilibrium, which has OH minus in it, if we only know a Ka? There's something wrong here, and a very important thing that we need to learn. And we'll see that, and we'll see what we need to learn in our next little episode here.